Good morning everyone. Welcome to the session. Myself Dr. Banala Saritha, Assistant Professor in the Department of Electronics and Communication Engineering, B.V. Raju Institute of Technology, Narsapur. Today we are going to discuss the course Digital Signal Processing and the topic is Introduction to Digital Signal Processing. What is a signal? So, a signal is defined as any physical quantity that varies with respect to time, space or any other independent variable. Signal is a measurable quantity that conveys information. Here I have provided an example, that is the function s1 of t equal to 7t, 7 into t, and the second signal s2 of t equal to 18 into t square. So these are the two signals which is represented in the mathematical form. So these two signals are depends on the independent variable time. So there are some signals which cannot be expressed by simple mathematical equations. So these are the various examples of natural signals. Most of the signals are natural signals. So the first natural signal we can say is a electrical signal. The voltage output of a amplifier is a electrical signal and the current output of the amplifier or a circuit is also a electrical signal. Acceleration of a car is the example of the mechanical signal. Air pressure measured by a microphone is the example for acoustic signal, and body temperature is the example for the biological signal. Intensity of each pixel is the example for image and video signal, and EEG, electroencephalogram, is the signal which indicates the brain activity, and ECG which records the heart activity, which is we can say as electrocardiogram. It is the one of the example for the natural signal, and EMG, it records the muscle activity. Electromyogram, it is also example for a signal. So these signals we cannot be represented in the mathematical form. So all these are the natural signals. So further the signals are classified into three types. The first one is multi-channel signals. Multi-channel signals are signals that come from multiple sources or multiple sensors. You can see the picture here. This is a EEG signal registered from different cortex locations. So here we are obtaining the four signals that is coming from the four channels. And the second classification is one-dimensional signal. So a signal which is a function of a single independent variable, we can say it is a one-dimensional signal. See the example of the one-dimensional signal, which is a speech signal. The third category of the signal is multi-dimensional signal. So a signal which is a function of two or more independent variable, we can say it is a multi-dimensional signal. So the intensity or brightness at each point is a function of two or more independent variable, let x and y is the we are called as special coordinates. So this is a multi-dimensional signal example. So I am consider the example as a picture signal where it contains x-axis as y-axis. We call as these are the special coordinates that denotes the intensity and brightness at each point. So these two are the spatial coordinates. So image is the example for the image or picture is the example for the multi-dimensional signal. And further the signals are classified according to the nature of the signal. So most of the signals encountered in science and engineering are analog in nature. Based on the characteristics of the signals, these are classified into analog signal, discrete signals and digital signals. Analog signal is also said to be continuous time signal. We'll see one by one. What is a continuous time signal or analog signal? So when the signal is defined continuously for any value of the independent variable, it is called an analog signal. That means the signal is continuously varies with the independent variable. I am saying a continuous signal that varies with respect to time. So that signal I can represent it as x of t, where t represents the independent variable time. So you can see the figure, this indicates the analog signal. So it is a continuous sinusoidal waveform which has the peak to peak amplitude 10 volts, positive side 5 volts and negative side is minus 5 volts. So this signal is continuously varies with respect to time. This is the example for the continuous time signal. And the second classification of the signal is discrete time signal. So when the signal is defined for discrete intervals of time or discrete intervals of any independent variable, then we can say it is a discrete signal. So discrete signals are continuous in amplitude but discrete in time. It is denoted by the x of n. Earlier continuous time signal is represented with x of t, where t represents the independent variable time, which is continuously varying with respect to time. But here it is continuous nature in amplitude but discrete in the time sequence. So we are representing the signal as x of n. So we consider these examples for the discrete time signals. Daily temperature, what is the minimum temperature and maximum temperature, and cricket score per each hour, and savings per month, pressure measured per every 2 hours. These are discrete in time. The values may be continuous, but we are measuring these values at particular intervals of time. So this comes under the category of discrete time signals. So this figure indicates the discrete time signal representation. Earlier we have seen continuous signal, which is a continuous sinusoidal waveform. So this is the example for the discrete time signal. So the discrete time signal is obtained by sampling the continuous signal with a particular sampling rate. And the third category of the signals are distal signal. So distal signals are discrete in time as well as quantized in amplitude. That means the amplitude is not continuous here, it is the quantized version of your continuous amplitude. So we can say distal signals are discrete in time and quantized in amplitude. And the examples for the distal signal are binary signal and Morse code. So if you consider the binary signal, it is used to represent the high amplitude as binary 1 or logic 1 and low amplitude with the binary 0 or logic 0. And the second one is the Morse code is the example. So where dot and dash are used to represent the sequence. So these are the classification of signals. Now coming to digital signal processing. Till now we are aware about what is a signal and what are the various types of signals like one-dimensional signal, multi-dimensional signal, multi-channel signal. Also what is a continuous time signal, discrete signal and digital signal. Now we'll move on to signal processing. What is signal processing? So signal processing is any operation that changes the characteristics of the signal. So those characteristics include amplitude, shape, frequency and phase of the signal. Now what is system? So a system is a physical device that performs an operation on the signal. The examples of the system are, this is only a few examples. You can consider any system examples. Filtering system, if I am considering a low pass filter is used to allow only low frequencies and rejects the high frequencies. That means it filters the high frequencies, it allows only low frequencies. Its filtering is also a system. And amplifier system, also modulation system are the examples for the system. Now what is digital signal processing? Till now we have seen signal processing, system and digital also. Now altogether what is a digital signal processing? So a digital signal processing is the processing of signals by the digital systems. So that digital system may be either hardware, software or firmware. So the examples of the digital processing systems are filtering system, amplifier system and modulation system. Now we'll see the basic block diagram and basic components of the digital signal processing system. See the block diagram which is displayed. It contains 3 blocks, ADC which stands for analog to digital converter, and the middle block is digital signal processor, and the last block is D2A converter, DAC. So we are providing the input signal to a ADC and we are getting output at the output of the DAC, which is a digital to analog converter. We can say the input signal with the ADC as the front end and DAC with the output signal as the back end. So the middle one is the heart of your digital signal processing system, which is a digital signal processor. Now we'll see the block diagram in detail with the help of all the blocks. First, the analog input is provided to analog filter and then it is given to the analog to digital converter and it is given to the digital signal processor, that may be either hardware processor or software processor, like hardware kit, or it is a software processor, and then followed by a digital to analog converter, and finally it is given to reconstruction filter. Now we will see one by one each block. All the signals available in the nature are analog form, which is continuously varying with respect to time. So first, by using a transducer that converts any form of signal into electrical signal. With the help of transducer, we are converting the natural signals into the electrical form. That electrical signal we are providing to the first block, which is an analog filter. So the function of analog filter is, it is a low pass filter that is used to band limit your incoming signal. Also, it is used to remove the high frequency noise. When it is band limited, it avoids the aliasing effect. Also, it removes the high frequency noise. Once your signal is band limited, you have to convert the analog signal into discrete signal or digital signal with the help of analog to digital converters. And we are aware about various types of analog to digital converters, that may be either direct type or indirect type. So, if you consider the direct type analog to digital converters, it may be either flash type or successive approximation or charge balancing or counter type or dual slope ADC. So you can use either of the analog to digital converters. It converts your continuous signal into discrete form. Once the discrete signal is available, you have to provide it to the digital signal processing. Whatever the operations you want to perform on the signals, that will be performed by the digital signal processor. You can use a hardware kit like TMS 320C 6713 processor hardware kit. Otherwise, you can use the processor also to perform the required operations. Once the processing over, again I want to display the signal in the analog form only, because in nature we are easy to understand the analog form signals. So we are using the digital to analog converter at the output of the digital signal processing block. Digital to analog converter converts your discrete signal into the analog signal. So we are also aware about these various types of digital to analog converter, like weighted resistor method and R to 2R ladder network and inverted R to 2R ladder networks. So you can use either of the digital to analog converter, and the digital converter output is not exactly same as the analog input. So it is a staircase waveform. The output of the DAC is a staircase waveform. So you have to smoothen those edges so that you will get the analog form. So in order to do that function, we are using the reconstruction filter. So reconstruction filter is a low pass filter which smoothens your staircase waveform and it gives the analog output. So this is a complete block diagram of the digital signal processing. In this way, we are taking the analog signals as input. We are process the signals in the digital form, and the digital processed output is converted into the original analog form with the help of the reconstruction filter and DAC. This is the complete processing system. Now we will see the advantages of the digital signal processing. So the first advantage is it is cost effective. The digital hardware are compact, reliable, less expensive and programmable, and it is very much flexible. Since the DSP systems are programmable, the performance of the system can be easily upgraded and modified. And processing also easy. By employing high speed, sophisticated digital hardware, higher precision can be achieved in the processing of signals. And easy storage. The digital signals can be permanently stored in magnetic media so that they are transportable and can be processed in non-real time or offline. So these are the various advantages of the digital signal processing over analog signal processing. We will see the applications of the digital signal processing. Digital signal processing finds numerous applications. Here few applications are listed like speech processing applications, communication, biomedical, consumer electronics, seismology, image processing. We are used the digital signal processing techniques. However, digital signal processing suffers with some limitations. Those are system complexity is more due to the presence of A to D converter and D to A converter. So, if you recall the block diagram of the digital signal processing, it contains analog front end as well as the back end. So, the front end contains analog filter as well as analog to digital converter, and the back end contains digital converter with the combination of the reconstruction filter. So, the complexity of the system is more. So, this is one of the limitation. And the second limitation is bandwidth is limited by the sampling rate. So, you are converting the analog signal into digital signal by performing the sampling rate, by performing sampling. So, here the sampling rate is fixed. So, the bandwidth also fixed. This is also one of the limitation of the digital signal processing. And the third point is more power consumption is required. So, this is about the digital signal processing basic block diagram, advantages, applications and limitations. Now we will see the various methods to represent any discrete time signals. Representation of discrete time signals. So there are various ways, basically 4 ways to represent the discrete time signals. The first way is functional representation, second way is graphical representation, and third one is tabular representation, and another one is sequence representation. We will see one by one. Functional representation. In this functional representation, the signal is represented as a mathematical equation. So, I will provide one example. See this example. X of n amplitudes are provided, also the corresponding time index is also provided. See, at n indicates the time index, at n equal to minus 2, that means time index minus 2, the amplitude is minus 0.5. At time index minus 1, the amplitude is 1.0. At time index 0, the amplitude is minus 1.0. At time index 1, amplitude is 0.6. At time index 2, n equal to 2, the amplitude is 1.2. At time index 3, amplitude is 1.5. And the rest of the cases for other values of n, the amplitude is 0. If you represent any discrete time signal like this, we can say it is a functional representation. And the second representation is graphical representation. In graphical representation, the signal is represented in a two-dimensional plane, x-axis and y-axis. So, the independent variable is represented in the horizontal axis and the value of the signal is represented in the vertical axis. You can see the example for the graphical representation. So, at time index 0, the amplitude is minus 1. So, I have drawn a sample with towards the negative side. At time index 1, the amplitude is 0.6. So, I have drawn a sample towards the positive. Like this, if you plot the graph wise, we can say it is a graphical representation where x indicates the independent variable index time index n and y indicates the amplitude of the signal x of n. And the third way of representation is tabular representation. So, in tabular representation, the two rows of a table are used to represent a discrete time signal. So, one of the row is the time index and the second row is the amplitude of the discrete time signal. See this one example. I have drawn a table with two rows. First row indicates the time index n and second row indicates the amplitude of the signal x of n. So, for each time index we have represent the amplitudes. Just see, at n equal to minus 2, the amplitude is corresponding amplitude is minus 0.5. At n equal to minus 1, the amplitude is 1.0, like that. And the fourth representation is sequence representation. In sequence representation, The discrete time signal is represented as one-dimensional array. I have provided the example. Just see the example. This is the sequence representation of the x of n. X of n equal to, it's a sequence. All these samples represents the amplitude. But how to consider the time index? Usually the starting time index is represented with a arrow. So here I have taken at minus 1.0, the time index is 0. So you have to place a arrow downward to the minus 1.0. Okay. So this represents the sequence representation. This is about the today's session. Thank you one and all.
Like, share and subscribe. Hit the bell icon for more updates.